Hi everyone, Miss Bung here. Today we are learning about the area of regular polygons. So this is lesson 11.4 in our textbook, and we'll continue with 11.4 tomorrow. So let's go ahead and maybe just look at some regular polygons to review what those really are. Now we'll formally define these in just a moment, but you might recognize this type of diagram from a few chapters ago. We looked at regular polygons and drew some lines kind of like this, these diagonals, to separate our various polygons into triangles, just using the diagonal lines, non-overlapping diagonal lines. Now that was helping us determine, based on how many triangles we see inside of each shape, what the interior angle sum of our various polygons were. Now we're kind of going to be doing a similar thing here in order to determine the area of these shapes, but we're not going to be using diagonals to separate our shapes into triangles. We're going to be drawing a center point and drawing what we'll call radii to split our shape into triangles. So for example, here's kind of what some of our shapes will end up looking like. All of these may be congruent, maybe isosceles triangles drawn inside of our shape. So if we can find the areas of these triangles, then we can then multiply by some number to figure out what the area of our whole polygon is. That's essentially, very briefly, where our future formula will come from. But let's get some definitions first. So as a reminder, a regular polygon is going to be some polygon, a closed shape, with all congruent sides and all congruent angles. Now, like I said, it's going to be helpful for us to be able to talk about the center and the radius of the regular polygon. So we're going to be able to determine those parts by using a circumscribed circle. So the circumscribed circle, again, this is a reminder from last chapter, means the circle is touching all of our vertices of the shape. So you'll notice here that points A, B, C, D, and E, all of the vertices of this pentagon, they're all on the circle itself. So we would say that circle P is circumscribing this pentagon A, B, C, D, E. So that's important. The center of circle P is also the center of the pentagon. The radius, maybe PA or PB, is also the radius of my pentagon. So the radius will be basically from the center out to a vertex. So we can't just say like any old point anywhere on the side. It does have to be a vertex. Okay. Now the next word is a little funky. This one might be new for us, and that's apothem. So our apothem is going to be a perpendicular segment, that's especially key, drawn from the center, P in this case, of our polygon, to the side, any side. We have one drawn here. This would be an apothem. So notice it starts at center P, it goes out to side AB, and it is perpendicular to that side. So a non-example of an apothem would be like P out to, let's just say this point is X, and this is not a 90-degree angle. That would not be an apothem. It has to be perpendicular to the side. So the apothem is especially helpful because it represents the height of this isosceles triangle. We have an isosceles triangle here existing inside of my pentagon. So I'm just going to sketch that triangle, maybe flip it upside down. We know that, let's see, this is my point P. We'll say this is A and B. We know that PA and PB are congruent because they're both radii of the same circle and of the same pentagon. So at the very least, we know this is going to be isosceles because at the very least, two sides are congruent to each other. So let's say AB, we would call that perhaps the base of this triangle, which means PF would then be the height. Remember, it has to be perpendicular. The height always has to be perpendicular to the base. So I'm thinking I could find the area of this triangle. I could say perhaps the area of this little isosceles triangle is equal to, okay, 1/2 times base times height, 1/2 times the length of AB times the length of PF, or the length of, let's see, the side of my pentagon times the apothem. Okay, I wonder how many of those isosceles triangles we could potentially fit in. You might be seeing where we'll come up with our formula. We'll get there in a moment. There's one last vocab word that I want to go over, and that is central angle. Should sound familiar. We talked about central angles when we talked about circles, and it really is almost the same exact thing. As you might imagine, a central angle must have a vertex right at the center of, this says angle, should say polygon. So our central angles in this pentagon will all have their vertices right at point P. So the other requirement then is that the sides of our angle have to pass through vertices of the polygon. So for example, APB, this angle here, would be a central angle. A non-example of a central angle would be like FPB, because point F is not a vertex of my pentagon ABCDE. So I'm only looking at the angles that, again, start at the vertices of my shape. They have to be consecutive vertices or next to each other. And then the vertex of the vertex of the angle is the center of the circle. So here's one. If I were to draw an extra radius here, here would be a central angle, so on and so forth. Okay. So the measure of a central angle in a regular polygon is going to be given by whatever n is, n representing the number of sides my shape has, 360 divided by n. You may hear my cat running around. So there will be n number of these central angles that we could draw. So for example, let's put those extra radii back. Those are the only radii I can draw for my pentagon. There's only 5 of them because there's only 5 vertices. There's also only 5 central angles. So if this is a full circle, then we can divide that evenly up and determine how many degrees each go for one. So 360 divided by 5 would get me the measure of this angle. Okay. So central angles, apothems, centers and radii of polygons, and of course our regular polygon. Let's give that just a little bit of practice before again we dive into the formula for our area. So I would recommend sketching out this diagram we have on the right and pausing to answer the 2 questions below. I'll give you a moment. Okay, so let's go over this. Our first question says to determine the measure of a central angle of a regular pentagon. Oh, we were just looking at a regular pentagon. So let's see if I can sketch that. That sounds like a challenge, but we'll do our best. Here's a circle. Ooh, that's terrible. Let's try that again. Oh, I'm getting worse and worse. Okay, whatever I draw this next time, that's going to be it. All right, somewhat better, whatever. Here we go. Here's my regular pentagon. This is really where having a geometer is super helpful. We're going to pretend that that's regular and perfect. we want to know what is the measure of my central angle. So again, if I draw my little center point and draw two radii, two consecutive vertices, what is the measure of this angle? So just what we were looking at in the last diagram. That is going to be given, of course, by 360 divided by n. N in this case, of course, is 5. So let's see, 360 divided by 5, it's going to be nice even 72 degrees. All right. So for number 2, we needed to use the diagram at the right of square FGHJ. Excuse me. Oh, I promise it's not coronavirus. Okay, just been talking a lot. Okay, so it's inscribed in circle K, or in other words, circle K is circumscribing the square. So the center of the square is the same as the center of the circle, point K. A radius, well, we've got a couple options. We could say KG is a radius, or GK, or we could say KH. Oop, let's make one of those a K. KH or HK would also be a radius. Either of those is fine. An apothegm. The only one drawn here is KL. Again, starts at the center, is perpendicular to one of the sides. Therefore, a central angle, we'll name it angle GKH, could be angle HKG. And the measure of the central angle, well, okay, this is a square, so n is equal to 4. So 360 divided by 4 is just going to be 90 degrees. So it just so happens that our interior angle and our central angle are the same. We won't usually see that. I wouldn't say that's like a rule to look out for. Okay, let's go ahead then and introduce our formula. So our formula for the area of a regular polygon, there are really a few ways to write this. We have involved in this formula the length of the apothegm, the number of sides, we'll call that n still, and the side length. Remember, for a regular shape, that side length applies to all, however many sides there are. So in this case, all 5 sides. So our first formula is given here. A is equal to 1/2 times the apothegm times the number of sides times the side length. So I might start by again pointing out, like we've been maybe building up to, that we could very easily find the area of this isosceles triangle. Remember that we labeled this our radius. For now, I'm just going to call that R. So this would be an isosceles triangle. If this side length up here is S, then this side length down here is also S. So the area of just this one isosceles triangle is going to be A times S over 2, or 1/2 times A times S, where the apothegm again represents the height and S represents the base. So maybe I'll write that area of the triangle is equal to this. So as we were getting to on the previous slides, we can draw a total of 5 radii in a pentagon, or perhaps we would want to say a total of n radii for an n-gon, which means we're also able to then draw a total of, or divide my shape up into a total of n congruent isosceles triangles. Here's one, we've already found the area of it here, 2, 3, 4, and 5. So if we already have 1/2 times the apothegm times the side length, then we just need to multiply that by n the number of sides or the number of these triangles in order to get my total area. So that's where our 1/2 times A times N times S, or honestly it could be 1/2 times S times A times N. The order of these really doesn't matter at all. That's where that comes from. Now another way that we can represent our area formula though is here. Area is equal to 1/2 times A, still the apothem, times P, where P is the perimeter of our polygon. And the reason behind that is, well, okay, we're given, again, our side length sometimes, and we can find the perimeter of our side length, or the perimeter of our polygon, not of our side length, the perimeter of our polygon by multiplying that side length by n. Because again, we're counting how many sides are there. There's 1, 2, 3, 4, 5. They're all S because this is a regular polygon. So S times N or N times S is equal to the perimeter. So in some problems, we just want to think about, okay, what's the perimeter? And then what's that apothem? We can multiply that together and multiply it by 1/2. That is still doing this math over here where we're really finding the area of these different isosceles triangles, but it can change depending on what you're starting with in a given problem. Okay, so let's do a couple of examples. Let's look at a particular, did I do a pentagon next? I think I have, oh yeah, okay, we've got a hexagon here. And we're not given the full name, so whatever. We do want to find the area of this. So the area of this hexagon, let's think about what we have. We know that S, our side length, is equal to 3. We don't have A yet. A would be the measure here of BD, so we're going to need to figure what that is. But we do have N, N being, of course, just the number of sides. We could count those. We could see that this is a hexagon, so N has to be equal to 6. So I'm going to need to figure out then what the length of this apothem is in order to determine my area of the circle. So in order to do that, let's think about perhaps what I've got going on here. What is the measure of my central angle? I think that's going to be helpful here. So my central angle, angle ABC, how do I determine that? Measure of angle ABC. Well, it's a central angle, so it's given by 360 divided by n, or 360 divided by 6, which is a nice even 60 degrees. I like that. I like that this is 60 degrees. I already knew that these being radii, this is an isosceles triangle. Because in its isosceles, I also know that these base angles are congruent. Okay, so if those are congruent and this angle is 60 degrees, well, in fact, this triangle is not just isosceles, it is equilateral. Notice that I could determine that by maybe calling these like x. They're congruent, so they would both be x. So 60 plus 2x would have to be equal to 180, or 2x would be equal to 120, and x would still be equal to 60. So if you're wondering how we can just jump to that conclusion, there is a justification there. Okay, so let's go back to the fact that we know this is an equilateral triangle. That makes this relatively simple to solve. Because if this is an equilateral triangle, then first of all, I know that these sides are also 3. In fact, the radius of my hexagon is also 3. And I know that this height of my equilateral triangle, or of my isosceles triangle, not only is it perpendicular to my base, but it is also the segment bisector. So A to D and D to C, those are congruent. It's a segment bisector. It is also an angle bisector. So these little angles up here are congruent. All things that happen, again, when we have the altitude of an isosceles triangle drawn. Very fun stuff. Okay, so based on this fact, I know that this little angle, let's see if I can switch colors to something helpful here. Maybe we would call this angle DBC, measure of angle DB, let's see. Okay, we're back. I think I froze things for a second. Measure of angle DBC is equal to 30 degrees. So this happens to be a 30, 60, 90 special right triangle. So I can determine the length of A based on the ratios of a 30, 60, 90 special right triangle. This looks a little crazy. I'm going to get rid of that. Now I could use trig as well. Honestly, this being a right triangle, this little guy here being a right triangle, I could use trig to solve for A, but I mean, either way, honestly, maybe we'll do both. So remember that in a 30, 60, 90 right triangle, we know that the side lengths have the following ratios. Our shortest side, we could call, maybe we'll call it X, is to our hypotenuse, which is 2X, which is to our longer leg, which is X root 3. So I'm given the hypotenuse. I'm given that 2X is equal to 3, which means X is equal to 3 over 2. So then I can figure out what my longer side is. Remember, that's actually what the apothem is. A is equal to X, that's 3 over 2, times the square root of 3. Or perhaps another way to say that is 3 root 3 all over 2. Okay, so now I know that apothem. Took a little bit to get there, but I know what it is now. We could have used trig as well. We could have said that the, let's see, what do I have? My hypotenuse and my opposite side for this 60 degree angle. The sine of 60 degrees is equal to the opposite, that was A, over 3. That's my hypotenuse. That would get me the same result. If we put that all together, let's write our area formula over here. The area of this regular hexagon is equal to 1/2 times A, 3 root 3 over 2, times maybe N next. We could do S first, whatever. 6 times 3. So we could maybe figure that out in exact terms and then plug it into our calculator to figure out a decimal approximate form. So let's maybe think about, we know this is 18 and 1/2 times 18 is 9. So let's see, area is actually, let's get that out of the way. It's actually 9 times 3 root 3 over 2, or 27 root 3 over 2. Okay, that doesn't give me maybe a great sense of how big this shape actually is. Of course, our units are meters squared, square meters. So maybe I'll just plug that into my calculator. It doesn't necessarily say what form we want our answer to be in, so maybe I'll just try both. So 27 times the square root of 3, all divided by 2. I get here 23 point, let's round to the nearest hundredth, 38. Again, square meters or meters squared. All right, let's do one more. One more where maybe we focus on doing trig. Here's our pentagon. Okay. So we are not given our side length. We are only given, in this case, our radius, which is 10 inches, and the fact that this is a pentagon. So n, that's the easiest thing perhaps to identify, is equal to 5, but I don't know A, the apothem, and I don't know S, the side length. I need to find both of those. So in order to do that, again, I'm going to need to use this central angle. I'm going to need to use some trigonometry, in fact. So let's look at the central angle. We calculated this in a previous example, but the central angle for a regular pentagon is 360 divided by 5, or 72 degrees. So we know that that angle, perhaps QPR is what I would call it, is equal to 72 degrees. And again, this being an isosceles triangle, I also know that angle RPS is congruent to angle SPQ. That is because we've got an altitude PS drawn in this isosceles triangle, meaning that it is not only an altitude, it is an angle bisector, it is a segment bisector, etc. Okay. That also means that if this whole angle is 72, then I can say that each of those little angles are 36. So measure of angle, we'll call it RPS, is 36 degrees. Now I'm just going to sketch maybe off to the side here this little right triangle. I'm interested in that little right triangle for now. It's not really to scale, but that's okay. I know that the hypotenuse of this right triangle is 10, and that this little angle is 36 degrees. I could find this other angle. I'm not sure I really care about it so much. But what I do care about is figuring out what is this apothem and what is this length, which I could call 1/2 of S. Let's see if I can write that a little bit better. Maybe in fact I'll call this X, but say X is equal to 1/2 of S. Because again, our apothem piece here represents the altitude and the angle bisector, the perpendicular bisector, blah, blah, blah. Okay, so in order to solve for these various measures, I'm going to need to use trigonometry. So let's think about maybe solving, I don't know, for A first. It doesn't really matter which we do first. So with reference to our 36-degree angle there, I've got A, which is, of course, adjacent to that angle, and my hypotenuse is 10. So that means I can write the equation cosine, adjacent over hypotenuse. Cosine of 36 degrees is equal to A over 10. So 10 times the cosine of 36 will be equal to A. So let's maybe plug that into our calculator. It doesn't say, but I'm going to go ahead and round to the nearest hundredth. So 10 times cosine of 36, I get 8.09. 8.09. Okay, same idea for X. Except this time X, well, that actually represents the opposite, of course. So the equation I want to write is involving sine. Sine of 36 degrees is equal to opposite over hypotenuse, X over 10. So 10 times sine of 36 is equal to X. Let's go ahead and plug that in. 10 times the sine of 36 is equal to 5 5.877 or 5.88. Okay. Remember that x was only half of my side length s. So I actually need to multiply x by 2. I need to say 2 times 5.88 is equal to x. Or, let's see, 11.76. Is equal to, sorry, not x, this is equal to s. Just realized I used the wrong thing there. Okay. Aha, so we have all our needed information. Got 8.09 for our apothem. We have 11.76 for our side length. All right, so our formula reads area is equal to 1/2 times, let's do n first. Again, it doesn't matter. 5 times, let's do the apothem next, 8.09 times 11.76, our side length. And if we plug that in, 0.5 times 5 times 8.09 times 11.76, I get a grand total of 237.8, again, I'm going to round to the nearest hundredth, 0.85. And my units there are square inches. All right. So you'll notice, and there are examples here, we needed to use some trigonometry or knowledge of special right triangles and use that central angle in order to determine some of the necessary information. So not as always just straightforward as, you know, plugging in your apothem, plugging in your side length. Sometimes you actually need to solve for those. Okay, have fun with these. I will let you go for now.